All right, welcome to the deep dive. Today, we're going on a bit of an adventure, I'd say, into the world of iron recovery.
An adventure is right. It's amazing the stuff you've dug up. A whole pile of scientific articles about getting iron back from, well, just about everything, it seems like.
That's the goal, right? To not just skim the surface, but really see what makes each method tick. Find those key insights and share them with our listeners.
Definitely. And you've provided such a range, it's fantastic. We've got computer models, like seriously complex ones, that map out how solvent extraction works.
Oh, yeah, and those optimization puzzles they're tackling with iron precipitation, how to balance cost and efficiency. Don't forget that historical angle, too, the whole story of iron electrowinning.
Plus, we've got deep dives into the chemistry behind different extraction techniques. A real treasure trove, honestly.
So, for our listeners, consider us your guides. We're going to break down the tough stuff, highlight the surprising bits, and try to make those connections between the science and what it all means in the real world.
And something that really struck me going through these articles is how these technical details, they really have a big impact.
Yeah.
I mean, on cost, on the environment, it all matters.
Yeah, you don't always think about it, right? Like just moving iron from one liquid to another, that's solvent extraction in a nutshell.
But there's a whole lot of chemistry going on there, a real dance of molecules. And scientists have come up with some pretty amazing models to describe it.
So we've got these three main types of models, right? First up, theoretical models built on, well, theory.
The core chemical principles, they aim to explain the extraction process based on, the reactions happening at the atomic level.
Then we've got the semi-empirical models, which are kind of a hybrid approach.
They borrow ideas from things like adsorption, where molecules stick to surfaces, or vapor-liquid equilibrium. Remember Raoult's law from chemistry class?
Vaguely.
So these models, they use observations from the real world to refine the theoretical framework. Not purely theoretical, but not completely data-driven either.
Right. And finally, we have the totally empirical models. They're basically about finding the best mathematical equation to fit the experimental data.
Like you've got copper extraction using LiX64N, or lanthanum and yttrium with specific extractants, even molybdenum and tungsten extraction using a combination of chemicals. It's all about finding that perfect curve.
Now, when you're trying to model these real-world industrial processes, you run into some snags.
Snags is an understatement. Like predicting the pH accurately in those countercurrent systems, that's where two streams flow in opposite directions, multiple stages. It gets tricky because these solutions are super concentrated.
Salt City.
Yeah.
And those high salt levels, they mess with the theoretical pH prediction.
Yeah, so the researchers, they had to get creative. They observed how much iron was extracted and then connected that to the actual pH changes they saw. That gave them a relationship, an empirical one that they plugged back into their models.
So it's not just about the theory. You got to have that real-world data.
Exactly. To get a model that actually works, you need both the theoretical foundation and the real-world adjustments.
Speaking of real world, let's talk about those key variables in the countercurrent extraction process. Like, what knobs can we turn here?
Okay, so you've got the phase ratio, which is just how much of each liquid you're using. Then there's the number of stages in that cascade, how many times the liquids are mixed and separated. And of course, you've got the iron concentration.
Iron concentration where?
In both the raffinate, that's the treated aqueous stream after extraction, and in the loaded organic phase, the one carrying the extracted iron.
Okay, 4 variables. That's a lot to juggle.
It is, and the tricky part is you can only really control 2 of them independently. The other 2 are determined by, well, chemistry, by how the system naturally wants to reach equilibrium.
So you set 2, the other 2 fall into place. Sounds like a puzzle.
And that's where the computer simulations come in. They help figure out what happens to those other variables when you tweak the 2 you're controlling. It's a bit of a digital trial and error process, but it's way faster and cheaper than doing it all in the lab.
Absolutely. But of course, you still need those lab experiments to get the data in the first place. What did the researchers do there?
2 main types of experiments. First, you've got batch equilibration. It's like take your organic phase and mix it with fresh portions of the aqueous solution over and over at a specific ratio.
Why do you need to repeat it?
Because a single contact might not tell the whole story, especially when you're looking at how pH changes affect the amount of iron extracted. You need that repeated exposure to really map out the relationship.
Okay, so it's like building up a comprehensive picture. What's the other experiment?
That's the continuous flow setup, using a mixer settler unit. Imagine a series of chambers where the 2 phases are mixed, allowed to separate, then moved along to the next chamber.
So it's a miniature version of a real industrial process.
Exactly. It lets researchers study how the extraction performs under more realistic conditions. And all this data then feeds back into those models we talked about, making them more accurate and reliable.
So what's the big takeaway? Why go through all this trouble with models and experiments?
The power of prediction. That's the key. A good model can tell you what will happen in situations you haven't actually tested in the lab. And that's huge for designing and optimizing processes.
That makes sense. Why waste time and money on 1,000 experiments when a good model can give you a pretty good idea of what to expect?
Exactly. You can play around with different pH values, different numbers of stages, different concentrations, all in the computer, and find the most efficient and cost-effective way to run the process.
Speaking of specific examples, one of the articles goes deep on extracting ferric iron, Fe3, using Versatic 10. That's a particular kind of extractant.
Oh, yeah, that one is fascinating. They use this system called AKUFVE, really precise, to measure how iron distributes itself between the liquids at different concentrations, all while keeping the pH steady.
Steady pH, that's always important. What did they find?
Well, first they tried the usual slope analysis, a classic technique in this field. But it didn't quite work because the Versatic 10 complexes in the organic phase, they were just too complex,
Too many moving parts.
basically. So they went with a statistical approach, crunching numbers to figure out what those complexes actually look like and how strong they were.
And they used infrared analysis too, right? To check their results.
Yeah, it's like shining a light on the molecules and seeing how they vibrate, which tells you about their structure. And you know what? The statistical models and the infrared analysis, they lined up pretty well.
Okay, so what did this combination of techniques reveal? What were these complexes like?
Hold on, it gets a bit technical. The complexes generally followed the formula FeOH3 and VNSHV, where N is the number of Versatic anions attached to the iron, Ns is how many Versatic molecules are just hanging around, and X tells you if it's a monomer, dimer, trimer, and so on.
So it's not just one iron atom grabbing one Versatic molecule. There's a whole party going on.
Exactly. And they found that N could be 1 or 2, S could range from about half to 2.5, and these values tended to go down as more iron was loaded in. The X was usually 2 or 3, suggesting that dimers and trimers were the main players.
So lots of iron atoms clumping together with Versatic. What else did they learn?
They looked at how long it took to reach equilibrium, and that varied depending on the pH, anywhere from 12 to 18 minutes. Another interesting thing, even with all that aluminum nitrate in the solution, the pH still needed some adjusting.
You'd think that much aluminum would act as a buffer.
You'd think so, but they had to add sodium hydroxide to keep the pH in the sweet spot. 1 or 2 moles in NiH for every mole of iron extracted.
So pH control is crucial no matter what. They also had some equations, right? Like equation 2 and equation 3, relating the distribution ratio to different factors.
Right. Equation 2 basically shows how the distribution ratio, which tells you how much more iron prefers the organic phase, is affected by things like the iron concentration in the water, the pH, and how much Versatic acid is in the organic phase. It also takes into account those N's and X values we talked about.
And that equation, it backed up their other findings.
Yeah, when they plotted the data a certain way, the slope of the graph was about 2, which suggests that each ferric ion likes to hang out with 2 Versatic anions.
Like a two-handed handshake. What about equation 3? What does that tell us?
That one helps figure out the polymerization number, X. They looked at the pH where the distribution ratio hit 0 and saw how that changed with the total iron concentration. That gave them an X of around 2, again pointing to those dimers being the main form.
Okay, so more evidence for those iron buddies. Did they find anything else interesting?
They found that more Versatic acid in the organic phase was a good thing. I'd pull out more iron. But there's a limit. If you go too high, it gets harder to separate the two liquids cleanly.
Practical limitations. Always something to consider. They also figured out the solvation number is, right?
Yeah, they plotted some data, looked at slopes, and got an ES between 0.64 and 0.88. But then they went even further, using computer programs to test all sorts of combinations for N's and eggs to find the ones that fit their data best.
A brute force approach.
They even used statistical tests to see which specific complexes were most likely to be present.
So a really thorough analysis. What conclusions did they draw from all of that?
Well, they felt most confident about the N value, the number of Versatic anions bound to the iron. They also confirmed that dimers and trimers were the dominant species, though monomers could exist too. But here's the interesting bit. They realized that sometimes using non-integer values for N's and eggs gave the best fit to the data,
What does that mean, non-integer?
like 1.5 instead of just 1 or 2. It suggests that there's probably a mixture of different complexes all coexisting in the organic phase.
Makes sense. It's not just one type of complex ruling the roost.
Exactly. They also concluded that those complexes with 2 versatic anions per iron, like Fe2OH, are the most common. Unless there's a ton of iron present, then FeVOH2 becomes more important. And here's another trend. Both N-enhanced ends tend to decrease as the iron concentration goes up.
So the type of complexes that form, it's not fixed. It changes depending on how much iron is around. Dynamic stuff. And they use that infrared analysis to confirm all this.
Oh yeah. The infrared spectra, they showed the fingerprints of different chemical bonds. They could see the versatic acid dimer, the monomer, and the bands that indicate the versatic anion is actually coordinating to the iron. One particular band, at 1415 centimeters 1, got stronger as the iron concentration increased, suggesting a specific type of binding called bidentate bridging.
Bidentate bridging.
It's like one versatic molecule is holding onto 2 iron atoms at the same time.
Yeah.
They also spotted some versatic molecules that weren't directly bound to the iron. They were just kind of hanging around.
Like a solvent entourage.
Yeah.
What did the quantitative part of the infrared analysis show?
That was key for confirming the molar ratio of versatic acid in the complexes. They found it went down from about 6 to 2.2 as they loaded more iron in. This really supported the idea of dimers and trimers with versatic acting as bridges.
Okay, so putting it all together, slope analysis, statistics, infrared, did they paint a consistent picture?
Overall, yeah, pretty good match. The compositions from the different methods agreed reasonably well, except for those solvation numbers. They think the slope analysis wasn't as accurate for that.
So the infrared was the tiebreaker.
In a way, yeah. And there was really good agreement between the bound versatic predicted by their models and what they measured with the infrared. That gives them a lot of confidence in their equilibrium constants.
Excellent. Well, let's shift gears now. We've been deep in the molecular world of solvent extraction. Next stop on our journey is dynamic optimization in iron precipitation.
Ah, yes, the goethite process, specifically in zinc hydrometallurgy. This is where things get really interesting. It's a real balancing act, a constant adjustment in real time.
So goethite is the target here. That's a form of iron.
Right, iron oxyhydroxide to be exact. And the way you get it is by adding oxygen and zinc oxide to a solution that contains iron. It's a controlled precipitation process.
Okay, controlled is the key word. Why not just dump a ton of those chemicals in and call it a day?
Because that's where the balance comes in. You want to remove as much iron as possible, but you also want to minimize how much oxygen and zinc oxide you're using. They cost money.
Ah, so it's a tug of war between efficiency and cost?
Precisely. And to complicate matters further, the chemical reaction that forms goethite, it doesn't happen at a steady rate. It's what we call first-order kinetics. The rate depends on how much of the reactants are present. So as the reaction proceeds, the rate changes.
So it's like trying to hit a moving target.
In a way, yes. That's why you need dynamic optimization. You have to constantly monitor the process and adjust how much oxygen and zinc oxide you're adding in real time to get the best result.
Okay, so how do you even begin to tackle that kind of problem?
Well, the researchers in one of the articles, they came up with a clever approach. They used what's called the discretization method. Instead of dealing with the process as a continuous flow, they broke it down into smaller chunks of time.
Time segments.
Exactly. And they focused on the control variables, those being the rates at which oxygen and zinc oxide are being added. Within each time segment, they treated those rates as constant values.
So it's like taking a series of snapshots of the process at different points in time.
Yes, that simplifies things a lot. It turns the continuous problem into a nonlinear mathematical programming problem that can be solved with computers.
Ah, right. Computers love those discrete problems. So they've got the problem broken down into manageable chunks. What next?
They then bring in a multi-objective optimization approach. They use something called the state transition algorithm, or STA for short, combined with constrained non-dominated sorting. It's a fancy way of finding the best possible solutions given the trade-offs between cost and efficiency.
Trade-offs meaning you can't have the best of both worlds.
Exactly. You can't just magically remove all the iron using the least amount of chemicals possible. There's always a compromise. So the algorithm finds a set of solutions, each one representing a different point on that compromise curve.
And then they have a way to pick the best solution from that set.
Yes, they developed an evaluation mechanism that takes various factors into account.
What kind of factors?
Well, first they lay out their optimization model mathematically. They define 2 objective functions, J1 for the cost of the chemicals, and J2 for the efficiency of iron removal. Then they identify the control variables, which are those addition rates for oxygen and zinc oxide in each of the 4 reactors they're using. And of course, there are constraints.
Constraints like what?
Things like flow rate, temperature, and the acceptable concentrations of different ions in the solution. Copper, ferric iron, ferrous iron, hydrogen ions, all that good stuff.
So it's like a recipe with strict limits on the ingredients.
In a way, yeah. And to describe the actual chemical reactions happening, they use dynamic equations that track how the concentrations of those ions change over time in each reactor.
Sounds like a lot of equations.
It is, but it's all based on fundamental principles, like the conservation of mass and the kinetics of the reactions.
Okay, so back to that discretization method. How does it work in practice?
They split the total time of the process into non-uniform intervals, meaning the lengths of those time segments aren't equal.
Not equal. How do they decide how long each segment should be?
That's the cool part. The algorithm actually figures that out as it goes along. It's not predetermined.
So it can adapt to the problem as it learns.
Exactly. And within each of those time segments, they assume the control variables, those addition rates, are constant. This turns the continuous problem into a discrete one, which is much easier to solve mathematically.
So it's like a series of steps instead of a smooth curve. You mentioned that state transition algorithm, the STA. What's so special about that?
It's a metaheuristic algorithm, which is a fancy way of saying it's a really smart search tool. It explores all sorts of possible solutions and uses different transformation operators to move around in that solution space.
Transformation operators. Sounds a bit like science fiction.
Kind of, but it's really just a way to systematically try different combinations of control parameters until it finds the best one.
Like a super efficient way to explore a maze.
Exactly. And once it's found a bunch of good solutions, those Pareto optimal ones we talked about, it uses that evaluation mechanism to pick the winner.
The evaluation mechanism, you said, it looks at trends in ion concentrations.
Yes, both the trends at the switching points between those time segments and the overall trends in the last reactor.
Why are the trends so important?
Because they tell you about the stability of the process. If the concentrations are bouncing all over the place, that's not good, even if the final values are within the acceptable range. You want a smooth and predictable process.
Right, consistency is key. But how do you deal with the fact that there's always some uncertainty in those measurements and trends?
That's where fuzzy logic comes in. It's a way to deal with things that aren't just black and white, true or false.
Fuzzy logic, like shades of gray.
Exactly. So they define linguistic variables for the concentrations, like very low, little low, stable, and so on. And they do the same for the trends, negative big, positive small, things like that. Then they have a set of fuzzy rules that link those inputs to an overall evaluation grade for the process.
So it's a way to capture expert knowledge about what makes a good process, even when things aren't perfectly precise. And then they can use this fuzzy system to pick the best solution from that Pareto set.
Precisely. The article even have a diagram showing the whole strategy. It's figure 8. It shows how the model, the algorithm, and the evaluation mechanism all work together.
Okay, and they compared their method, that MASTA thing, to another algorithm, the NSGAII. How did it stack up?
It performed really well, both in terms of finding good solutions and in terms of computational time. They have a table with the numbers, table 4, and the average execution times are very comparable.
So it's efficient. That's good. What about the actual simulation results? Did they prove that this dynamic optimization stuff actually works?
Oh yeah. Figures 9 through 13 show the results, and they're convincing. They were able to significantly reduce the amount of oxygen and zinc oxide needed, which translates to cost savings, while still meeting the quality standards for the final product.
Excellent. And they have a table comparing their method to manual control, table 5. It looks like they achieved a lower average iron concentration, better consistency, and, of course, less reagent consumption.
It's a clear demonstration of how optimization can lead to real benefits in an industrial setting.
All right, let's move on to our last big topic, electrowinning. This is where we use electricity to recover iron, right?
Exactly. The articles include a really cool account of the pyro process developed in Norway back in the mid-20th century. It was all about extracting every bit of value from copper-bearing pyrite ore, and electrowinning iron was a crucial step.
So electrowinning, basically, you're running a current through a solution to deposit iron onto a cathode.
Precisely. The pilot plant used iron starting sheets for the cathodes and lead anodes, separated by a diaphragm.
Why the diaphragm?
It's all about keeping things separate. At the cathode, you want ferrous iron, F2+ Mayen, to be reduced to metallic iron and deposited. But you also have side reactions, like hydrogen ions turning into hydrogen gas, or ferric iron, F3 plus mayhem, being reduced back to ferrous.
Okay, multiple reactions happening at the same time.
Meanwhile, at the anode, sulfate ions are oxidized, which regenerates sulfuric acid, and you get oxygen gas as a byproduct. Plus, some ferrous iron gets oxidized back to ferric.
So the diaphragm prevents those products from the anode from messing with the cathode reaction.
Exactly. You don't want oxygen gas or ferric iron near the cathode. They'll interfere with the iron deposition and reduce the efficiency. The diaphragm acts as a barrier, ensuring that the iron deposition process can run smoothly.
And the pyro process achieved a pretty good current yield, right?
Yeah, 85%, which is pretty impressive.
Yep.
And they did it with a power consumption of 4.25 kilowatt hours per kilogram of iron.
Not bad. They also mentioned adding salts to the solution, like sodium or ammonium sulfate. Why was that?
Two reasons. First, it boosted the conductivity of the solution, which helps reduce energy consumption. Second, and this is important, it improved the current yield.
How does adding salt improve the yield?
It basically reduces the amount of hydrogen gas produced at the cathode. The sodium and ammonium ions help carry the current, which means fewer hydrogen ions are available to be reduced. This also helps maintain a slightly higher pH, which is beneficial.
pH, again, always a factor. What were the specific findings regarding pH in this process?
They found that below pH 2, the current yield took a hit. But above pH 2.75, the iron deposit started getting rough, with dendrites and oxide inclusions, so they had to keep it in a narrow range to get both good efficiency and good quality.
A delicate balance. What about the current density and temperature?
Current density above 2.7 to 2.8 amps per square decimeter led to the same issues, rough deposits and dendrites. It's likely because the iron deposition becomes limited by how fast the ions can move to the cathode.
So you can push it too hard? What about temperature?
Temperature, within the range they tested, didn't affect the yield much. But a higher temperature did improve the smoothness of the deposit. They settled on 75 degrees Celsius as the sweet spot.
Okay, makes sense. The diaphragm material seems crucial too.
Absolutely. They tried all sorts of things, asbestos, stainless steel, but only got consistent results with fabrics made from vinyl chloride acrylonitrile or a specific type of terylene, even though small details matter.
And what about the electrodes? Iron starting sheets for the cathodes, but lead for the anodes, right?
Yeah, you need something that won't corrode away in that acidic environment. Pure lead wasn't quite strong enough, so they developed a special alloy with antimony and tin. It had a very low corrosion rate, something like 0.13 to 0.25 millimeters per year, which means the anodes could last for several years.
They even designed the anode with the sawtooth edge. Why was that?
It seems to help with the current distribution and the release of gas bubbles, making the process more efficient. They also welded it to a copper bus bar for better electrical contact.
Okay, so they put a lot of thought into the anode design. What about the operating conditions? What did those look like?
The feed solution had a pH of around 2 and an iron concentration of 55 to 65 grams per liter, mostly in the ferrous form. The cathlete was similar in pH, but with less iron, around 25 grams per liter. The analyte, on the other hand, had a higher iron concentration, with a significant portion being ferric iron, Fa3 plus iron.
What did they do with that ferric iron? It's not ideal for the process, right?
They treated it with hydrogen sulfide gas to convert it back to ferrous iron before recycling the analyte.
Smart. So what about the quality of the iron they produced?
They were aiming for a ductile iron with a smooth surface, something you could actually use for manufacturing. They noticed that if the iron concentration in the cathlete got too low, the deposit would crack and peel. Impurities like sulfur and hydrogen sulfide also cause problems, making the deposit rough. Even ferric iron in the cathlete, maybe from a leak in the diaphragm, would mess things up.
So purity and process control are key for getting a high-quality product.
Exactly. And the analysis showed that they did achieve very low levels of impurities, which is great. Plus, they did it all with reasonable energy consumption, 4.25 kilowatt hours per kilogram of iron.
Impressive. Okay, let's wrap up our deep dive with those alternative methods for iron elimination using precipitation. We've already touched on the goethite process, but the sources also describe the jarosite and hematite processes.
Right. These are especially important in zinc production, where removing iron is essential for maximizing zinc recovery. Jarosite precipitation is all about forming a basic iron sulfate compound. It's stable over a range of pH and temperature conditions, but ideally you want it around 95 to 100 degrees Celsius and pH 1.5 to 1.8.
And you need to stir things up, right? And maybe add some jarosite seed to help it along.
Yeah, that helps to get those nice well-formed crystals. The downside is that other metal ions like copper, zinc, cobalt, nickel, manganese, even some less common ones like indium, gallium, and germanium, they can get trapped in the jarosite crystals. Not ideal if you're trying to recover those metals too.
Right, it's like catching unwanted fish in your net.
Exactly. The conventional jarosite process was patented back in the early 1960s. It involves precipitating the jarosite at those high temperatures using sodium or ammonium ions. The reaction produces acid, which then has to be neutralized, typically using zinc calcine.
Zinc calcine, that's the roasted zinc ore, right?
Yeah. Yep. But using zinc calcine for neutralization, that can lead to some zinc losses, and other metals can be lost too. So people have come up with modifications like pre-neutralizing with zinc calcine and then washing the jarosite to recover more zinc. They even tried two-stage precipitation to improve things further.
Always trying to refine the process.
Absolutely. Now, the goethite process, we talked about that in detail already, so let's move on to hematite. This is where you precipitate iron as Fe2O3, essentially rust, at even higher temperatures and pressures. You need an autoclave, a specialized pressure vessel, to do this.
So hematite, high temperature, high pressure sounds intense.
It is. You're operating above 185 degrees Celsius and at pressures above 5 bar. The reaction releases acid, which needs to be neutralized, and you can get a byproduct called H₂SO₄ forming if the acid concentration gets too high.
Mm.
Plus, the presence of zinc sulfate in the solution can shift the conditions where hematite forms versus other iron compounds.
Sounds complicated.
It is, and it's expensive too. High capital costs for the equipment and high operating costs because of the energy needed to maintain those temperatures and pressures. But it does have one major advantage. It produces a very compact residue, which minimizes waste disposal problems.
So it's a trade-off, like many things in engineering.
Exactly. High cost, but low volume waste.
Okay, before we wrap up, let's touch on some of the other extractants that are used for iron removal.
We talk a lot about Versatic 10, but there are others out there. One that's been extensively studied is H₂SO₄, di-2-ethoxyl phosphoric acid. It's really effective at removing iron from zinc solutions.
But it has its quirks, right?
Yeah, the distribution ratio, that measure of how well it extracts iron, it drops sharply as the solution gets more acidic. And to strip the iron back out of the DEHP, you need a strong acid, like 5 molar sulfuric acid or 6 to 8 normal hydrochloric acid.
Strong acid's not always the easiest to work with.
Right. But there's a trick. You can mix DHP with another compound, PBP, tributyl phosphate, and that enhances the extraction. It's a synergistic effect. The two together work better than either one alone.
Interesting. What other extractants are out there?
There are the aminophosphoric acid extractants. They're really good at grabbing iron, even when there's a lot of sulfuric acid around. And they release the iron easily, so you can reuse the extractant. But there's a catch. Stripping the iron becomes difficult if the concentration gets too low.
So there's always a sweet spot for these things.
Always. And finally, we have the amines, like primine 81R. They work a bit differently, forming adducts with iron instead of just swapping ions. The solvent you use with them, the diluent, and any modifiers you add, they all play a role in how much iron can be extracted.
So lots of variables to tweak.
Yeah, and researchers are constantly working to find better combinations. The amines, they're promising, but there's still a lot of room for improvement.
So it sounds like iron recovery, it's not just one size fits all. There are all these different methods, each with its own strengths and weaknesses, and it's about finding the right tool for the job.
Absolutely. And the research continues. Scientists are constantly searching for better extractants, more efficient processes, ways to minimize waste and maximize recovery.
Well, I'd say we've covered a lot of ground today. From the intricate chemistry of solvent extraction to the optimization challenges of precipitation and the ingenuity of electrowinning, it's clear that iron recovery is a complex and fascinating field.
And it's vital, not just for the industries that rely on it, but for a sustainable future.
Absolutely. Now, for our listeners, we'd like to leave you with a thought. With all this focus on circularity and resource efficiency, how might these iron recovery methods evolve in the future?
Could we see completely new approaches emerge, maybe even driven by bio-inspired chemistry or nanotechnology?
And how might these advancements shape the future?